vessel. So how much is that?
Two.
There are actually two numbers we talk about. One is the brutto and second is the netto or working volume. The brutto is the absolute total volume of the reactor, which is 2.5 liter. Now the netto or the working volume is something like 60-70% of that volume. Okay? So typically we do not fill up more than 60-70%. I'm going to tell you why. So this is a glass reactor, as you see. Reactor can be made of steel or glass or something more recently from plastic, but typically it's from glass. It is double glass. It has a double wall. This double wall, it's also referred to as a duplicator. The double wall, the function of the double wall is to thermostate the reactor. Now if you are coming in, just come over. You see, this is a double wall, and it is connected to the fermenter here, and it is connected to the top. Just come over. There. Now, there is a thermostat. So there is a water reservoir inside this regulatory unit, and this water reservoir is can be thermostated. So the temperature of this water is set depending on the population, and so the water of given temperature is injected into this duplicator. This is how the fermenter, the vessel, is thermostated. Of course, temperature is critical. So technology-wise, it can be like up from 20 Celsius to up to 50-60 Celsius, depending on the strain. And it's very important because don't forget, any chemical reaction has a temperature optimum, and thereby any biochemical reaction as well has a temperature optimum. And also for any microorganism, it has a growth optimum. So even a couple of Celsius difference can be important. Now, how the temperature is measured? It is measured by thermometer. The thermometer is, I'm just sorry, it is fixed here, so I cannot remove from here, but it is typically working on the ability of metals to change the
Sorry, it's here.
Oh, yeah, yes, that's
Keep
it.
it for 10 minutes, okay? Just go quickly,
Okay.
sorry.
Okay. So yes, so this is okay. So this is the thermometer. You see, you can connect through this one. Somebody was very nice.
No, leave it.
And this is called the PT100 type of thermometer. PT stands for platinum, so platina, and the resistance of platinum will depend on the temperature, and this is what you measure. Okay, so this is how, and of course, if you are having 100, it is the ohm resistance of the metal. So this is how the temperature is set. Okay. Second is aeration. Now, aeration, just come over again.
Keep it.
Okay, you keep it.
Yeah.
We have air coming from the compressor room. I actually don't know where is it, but it is coming through this wall, and it is first there is pressure meter. So you have to set the pressure to something like 3-4 bars, and then the air is coming through this stage, and this is to decrease or to remove moisture from the air, because if moisture gets into the fermenter, the thing is not good. So you have to remove the moisture through here, and then you are also reducing the pressure to up to 1.5 or 1.6 bar. And then through this very long tube, it is getting into the fermenter and into this regulatory unit, and it is coming through this equipment here. Now, do you know what is this? It's called rotameter, and the rotameter is, you see, there is a small
Mercury.
it's not a mercury, actually. It is just a small.
Mercury is not allowed in
It's like a small ball here, and if you increase it, it's going upward, because there is air coming behind, and the air is pushing it up, and more air pushing it higher, less air pushing it lower. So you can control the amount of air, the airflow through this. If you look at that, I am increasing, and you see there are much more bubbles getting in. And if I am decreasing, there are much less air bubble getting in. So eventually I can even stop it, you see? There are just very few air bubbles there. Now there are much more air bubbles. Okay, right. And now the mechanical agitator is not running very rapidly. So it is only for mixing up the fermentation broth. So see what the bubbles, what the characteristics of the bubbles. Again, Kichi is showing me this. Okay, so the air is attached to this tube here, and it is going to the bottom through here, and you see there are very tiny holes on the semicircle here. Actually, I myself do not see it, but there has to be. So you see, there are some very tiny holes over there. Like you may see it, very tiny ones. And through those tiny holes, the air bubbles are coming out, and they are very close, physically very close to the mechanical agitator, and it is turning around, and they will immediately get in touch, they will get in contact with the agitator, and the air bubbles, the size of the bubbles will be reduced, the diameter will be reduced, and thereby from few big bubbles there will be many little bubbles. And of the many little bubbles, they have a very big surface area. And this is what matters because, I repeat, the mechanism through which oxygen is getting into the fluid from the bubbles is called diffusion. It's a diffusion process. And diffusion is proportional to the surface area that is available for the process. Okay? So immediately afterwards, the stirrer will get in touch with the bubbles and it will degrade them. It will just cut them in size. Teacher, I'm giving it back to you. Yeah. And now you are going to see what's happening. So these are the bubbles. So the one thing is that I can increase the airflow with the rotometer. But as I said, this is not very efficient. More oxygen will be coming out, but actually all the bubbles are moving up very rapidly. So this is not going to help us. But now you are going to see what's happening if I am increasing the agitation, okay? So, you see, first I am giving them like, so that's 200 from 50, and you can look at the bubbles. They are spinning up, you know, so the route they take is much longer because they are not coming up from the bottom to the top immediately, but they are doing in this rotary way, and so thereby they have more time spent in the liquid, and thereby they have more time for the oxygen to get out of the bubbles, because as I said, there are lots of oxygen in the bubbles and very little in the liquid, so the oxygen would be moving from the high concentration to the low concentration. So by itself it would be happy to move out, but it just can't because of this barrier at the surface here. So we need to increase the surface and give it more time, okay? So we are giving it more time for the bubbles. And now we are increasing up to 500, and you will see what a vortex means. Okay, so you see, this is the vortex. There is the axis, and you see it's like a funnel there, and you can see the bubbles. They are much smaller, but there are much more of them. Of the few big bubbles, now we have many small bubbles, and they are taking a much longer route while they are coming up. So this way we can increase the surface very efficiently, and we can give more oxygen to the system.
Just
okay. Yes, please.
Question. Does the size of the bubbles affect our yield?
Effect?
Yield, product yield, or?
Well, there is a correlation, I would say. But it's not the size of the bubbles, because it's very difficult to measure the size of them. You can see them, but it's very difficult to measure actually how big they are. what can affect the productivity in the dissolved oxygen concentration.
Okay.
And this is where I am coming on, that you have set up this system, and you can now quantify the overall mass transfer coefficient. Under these conditions, the fermenter the bioreactor has a rather high KLA value. So KLA, overall mass transfer coefficient, that's something you need to remember. But to quantify it for oxygen, you need a sensor. And we need an oxygen sensor, which...
It's not here, I think.
oh, actually, I saw it.
I saw it.
There was an oxygen sensor here. I saw it. Yes, please. Okay. So, I forgot it's empty.
Probably, it should be here.
Yeah, that's it. Okay. Yes, that's what I put. Okay. At pH, and this is okay.
That's the pH.
That's a pH. That's
That's
okay.
also a pH. Okay, the other one. That should be the right one. If it's heavy, the
Okay. So that's how DO sensor looks like. Actually, 10 times as expensive as the pH sensor. So, and it's also heavy. You know, it's not from glass; it's from steel. So you can even hit your enemy with it. And so that's quite heavy. And so of course this is for the bigger reactor, not for the small one. So, but anyway, you put it inside the fermenter through one of the ports, and with this sensor you can just measure the percentage of the saturation oxygen concentration in the liquid. So right now it is probably 100%, because under the current temperature and pressure, the oxygen is absolutely soaked up in water. So as much oxygen is in the water as it is possible, which is called 100%. And we can calibrate the sensor for this 100%. So the signal of the sensor will be calibrated as 100% under such conditions. And then afterwards, we are adding something like sodium dithionate, for instance, to the liquid, which will remove all the oxygen, so something that reacts with oxygen very rapidly, and that will be the 0%. You calibrate from 100% to 0%, and in between the sensor will give a proportional signal. And this proportional signal is measured and registered to the regulatory unit. So this is how you are measuring the DO. And DO is actually important. So this is just to answer your question. The technology, the effectiveness is not very dependent on the bubble size, but you cannot really measure it. What you can measure is the DO, the dissolved oxygen level, which means that how much percentage of the oxygen is there of the 100% of the saturation concentration. So that's it. Okay, the same goes for the pH. Now we have it here. So this is a pH sensor. That's of glass. And do you see something here compared to a typical lab pH sensor? I am keeping it this way.
There is something similar, like iron something.
There is electrolyte here.
Ah,
But electrolyte typically is a liquid, it's a fluid. But it's not here. It is a gel. You see?
yeah.
And so it is a gel, which we call it a gel electrode, and it is gel because you see? Okay. There is a diaphragm here, and through this diaphragm it is communicating with the environment. And so the protons which is the concentration of protons, is actually it is the pH. They are moving through this one. But of course, in the fermenter, there is a higher pressure than in the external environment, and this higher pressure may push the fermentation broth into the sensor, and it would just ruin it. So to prevent the contamination of the sensor through the diaphragm, you are creating a gel which has a higher pressure as well, so it will withstand this pressure. So this is a different type of electrode, and so different type of electrolyte. And therefore, this type of sensors are more expensive than the normal laboratory pH sensors. So this is for the fermenter. And now, I was talking about ports, which is ports. So a port is basically a hole on the fermenter, like, for instance, this is a hole here. You see? This is what we call a bigger port, and there are also smaller ports, but their size is always standardized. So it has to be and into these holes, all kinds of sensors can go inside, not only from this company but from other companies too. So there is a compatibility thing here, and so these holes are there on the fermenter to make us possible to immerse the DO sensor, the pH sensor, and the temperature. So these are the three typical sensors that are immersed: temperature, pH, and DO. And finally, there are ports, but these ports are designed to allow a sensor which is below the surface, below the liquid level. So they are immersed into the liquid. But these ones are actually in the headspace. So they are just basically getting through this top, but otherwise the stop rate, but otherwise they are not getting into the liquid. Now there are four of it, and this this is supported by these four pumps. One is for the acid, one is for the base, one is for the antifoam, and one is for, we call it level. Level is any substrate that you want to feed to the fermenter. What is why acid and why base? Because basically you are titrating the system. So you have a pH sensor immersed, it is measuring the signal, and if you want to get it higher, you are adding base. If you want to get it lower, you are adding acid. You have a set point, and of course the sensor gives a signal, and to the set point it is controlling through the pump. So it's either acid or base. So it's like a normal titration. But antifoam. Fermentation media has a tendency for foaming. It is because it might contain proteins, amino acids that are reducing the surface tension, and of course there is a lot of stirring. So altogether this will create foam, and foaming is dangerous because it can get out of the fermenter. So if it is really big, then it can move out of the fermenter, and it can cause contaminations. So you need to reduce foaming by adding antifoam. Again, antifoam is it's something like this. You are filling up this with antifoam, you are putting it here, you are connecting it with the pump, and you are adding it here. And you have an antifoam sensor, you have a foaming sensor, and this foaming sensor is measuring how much foam is there. It is about resistance. So imagine there is foam, the antifoam.
Is here.
Oh, it's here as well. Oh, very nice, Kichi. Okay. So this is the foaming sensor, that one. So typically, I'm just holding it up for you. So typically the fermenter is filled up to 60% of the volume. So this means that this is a little bit above of the normal level. So there is like a few centimeters between the water level and the sensor. Now this few centimeters is for the foam. If the foaming is too much, then the foam will touch this sensor. And by touching the sensor, it will make it wet. And this moisture on the surface will modify the resistance of the sensor, because it's made of metal, and the resistance of the metal is dependent also from the water content. The electrons will be moving more rapidly if they are wet. And it is the signal, and this signal will get into the regulatory unit and through it to the pump, and it will inject a few droplets of anti-foaming agent, and thereby the foaming size will be reduced.